And before we start talking about different source estimation methods and all the parameters involved, I thought it's a good idea to have a more general introduction to the EEG MEG inverse problem and why it's non-unique and underdetermined without too many equations. So let's just remind ourselves, first of all, there's the forward problem. So we only measure what the physics allow us and physiology allow us to measure. We want these primary currents, little batteries in gray matter. But then there are these volume currents that also produce magnetic fields and that ultimately allow us to measure electric potential differences at the scalp. So, and during this process, some information is already lost. So we will not get every individual neuron or dendrite. So we already need a few million of synapses to be active simultaneously, so to begin with. But apart from that, because we only have a limited amount of measurements, and because the physics has certain constraints, poses certain constraints on this problem, we can only expect to measure some information from these underlying sources and not everything. And we are trying to quantify this by creating these lead fields for our sensors. So I had this, I think, in the previous session already. So every sensor measures different dipoles across the cortex with different sensitivity, and the sensitivity we can quantify if we have a head model and use the physics of the problem, so we can determine how much of a signal would a unit dipole in this location with this orientation produce, and so on and so forth. So this gives us an idea of what we are actually measuring and how sensitive we are with our measurement. And with this information, we can then approach the inverse problem and see how much can we actually say about our sources when we have our measurements. And I would like to clarify that I actually don't think EEG and MEG are really scanning, or it's not really tomography. So at least not in the sense that we would use it when we are scanning with X-rays or with computer tomography. So the way I see, let's say, an old-fashioned computer tomography scanner, you have a choice where you send your X-rays through your body, and then it depends on you how many rays you send through the body, how many voxels you can then distinguish. So by, in this case, having 4 X-rays, you can divide your body into 4 quadrants, and then you can have your equations that say, well, the intensity of this X-ray depends on these 2 voxels in this direction, on these 2 voxels, and so on and so forth. And in the end, you get enough equations in principle, to solve these equations for all your 4 quadrants, for all your 4 voxels. And if you use 100 X-rays, you could potentially get 100 voxels. So it's an engineering problem, basically. Spatial resolution in that case depends on your on your methodology here. So how many X-rays you've got. And in principle, there is no problem with having these voxels either outside or in the middle of your brain. So you determine the spatial resolution of your method depending on how much money you can spend on your X-ray machine. And this is different with EEG and MEG. So here we are not sending anything into the body. We are only measuring what's coming out of it. We have our electrodes or sensors around the head, and we measure our signals. Usually we are most sensitive to signals that come from close by to the sensors. And also we know that signals will be smaller from within the brain when they're further away. For MEG, there are other reasons why sources in the middle of the head are less strongly detected. So this, I'm trying to illustrate that here. So your equations are already a bit imbalanced. So some sources produce more, you're more sensitive to some sources than to others. So you will have this imbalance already in your equations there. And also you have usually more sources here than you have sensors. But it's not, and apart from that, as we will see later, it's not just about the number of sensors. The physics of the problem already determine that certain information is lost in the measurement. So this is just something that we have to keep in mind. There is some information, there are sources or source configurations, distributions in the brain that do not produce any signal in our sensors. And this information can simply not be retrieved just with mathematics. So it's just not in the data. So, and this inherently limits spatial resolution of our measurements, on top of the fact that we only have a limited number of sensors and noise and inaccuracy in the location of these sensors and so on and so forth. So there are some fundamental differences, I think, between true scanning and tomography and the kind of inverse problem that we are dealing with EEG and MEG. But that doesn't mean that we can't do anything, of course. Stating the inverse problem, just like we did in a previous session. So here I'm just creating a very simple case. Let's imagine we have 3 sources in the brain that we are interested in, and but we only have 2 electrodes. Then we have this underdetermined problem where we measure from fewer sensors than we have sources in the brain. We can put all of this in a matrix equation. We have 2 data points. We have our lead field matrix. For every electrode, we have these values that tell us how sensitive we are to the different sources in the brain, a bit like this lead field, or actually exactly like this lead field vector that I had in previous slide. And then we have this matrix equation here. Data are the lead field times our unknowns. And we would like to get some, at least if we approach it with the linear method, we would like to get some inverse matrix here that we then have to multiply to our data, because we usually have the data. We want to know our dipole strengths. And this matrix is supposed to give us at least an estimate of what's happening inside the brain. And this is a pretty simplified, but still mathematically accurate description of how we approach our inverse problem with linear methods. The forward problem is linear anyway, so this lead field can be computed in different ways, but in the end, the relationship between the sources and the data is linear. We have a choice of many different inverse approaches, some of them linear or nonlinear. The most popular ones, I would say, are linear. And they will involve some sort of inverse matrix, like in this case. But we have to deal with the fact that this problem is non-unique. So we have more unknowns than we have data points. So we have to make some additional constraints to make sure we get a unique solution that is hopefully not too far off reality. So just to illustrate the non-uniqueness again, just imagine you have an equation with 2 unknowns. So in this case, whatever you choose in J1, J2 can be chosen accordingly to solve this equation. So that means you have infinitely many solutions. I mean, this is really just the simplest version of this kind of underdetermined inverse problem that we are dealing with here. And if we put this in a matrix equation, this is what you will see in many papers. Many papers start like that if they deal with linear source estimation. Data equals lead field times source vector. It could be time varying, so I really prefer to do it just for vectors here. The data are 1 vector, the sources are 1 vector, but in principle, data and sources can also have a temporal domain. And usually the number of dipoles is much larger than the number of sensors. So this could be in the range of thousands. This is in the range of maybe a few hundreds. Okay, to really hammer in the point what this non-uniqueness is, and that it's really a fundamental property of the problem, which you can't really overcome with any clever mathematics. So what is the solution of this equation? It's the same as we just had on our previous slide. There, I called it J, here I call it X, X1 plus X2 equals 1. Well, you could choose this or that, or in fact, completely crazy numbers. Whatever you do, you will always get, you can always construct a solution. And if you wanted to have a criterion to pick one of these many solutions, infinitely many solutions with some unique property, or that makes the solution unique, you could use the so-called minimum norm solution. Now I'm jumping ahead a little bit, but if you require the solution to this problem to be the one that is that has the minimum sum of squares of x1 and x2, so x1 squared plus x2 squares should be minimal, then you end up with these values here for this equation, 0.5, 0.5, which already shows that with this kind of constraint, you distribute the amplitudes evenly, or as evenly as possible, across all the different unknowns. And I compare that a little bit with the projection of a 3-dimensional image onto a 2-dimensional plane, or sort of 3-dimensional object onto a 2-dimensional plane. So as soon as you do that, the weirdest things can happen, like in these images by Escher. So you're losing information, but at the same time, sometimes you may see something in your data that is actually not there. So in EEG and MEG signal space, so without source estimation, we only see a faint shadow of activity in the source space. So we are losing information. We are projecting something from a higher dimensional space into a lower dimensional space. That means we still have some information, but we will not be able to reconstruct everything that created our signals. And just by way of introduction, so I just adapted this little quote from somebody else. If you're not shocked by the EEG and MEG inverse problem, then you haven't understood it yet. I mean, that is more or less what Niels Bohr said about quantum theory. But I think it is worth meditating over this a little bit. So especially when you are starting to explore the zoo of different source estimation methods, there are simply some fundamental limits to our spatial resolution, to the information we can get from our data. And you either have to live with it or you have to find a way to get additional information from elsewhere. But there is simply no mathematics or no clever algorithm that can get you information back that you've lost during the measurement. So now we can maybe go through a few examples of non-uniqueness that other people have described. And one of the big questions is, how deep can you go with EEG and MEG? So can you actually non-ambiguously distinguish superficial sources close to the senses from sources in the depth of the cortex or even subcortical sources? But there is already a fundamental non-uniqueness, namely that a deep focal source produces very similar, even the same signals like a distributed superficial source. So that means unless you have additional constraints on the focality of source or the distribution of your sources, you will not be able to say whether your source is close to the senses or further or deeper down, maybe more focal and stronger. So this is one important ambiguity that we have in our data. This is another example. So this illustrates a current distribution or dipole distribution. Imagine a patch of cortex that has over several square centimeters or so. And that produces exactly the same magnetic field as a dipole in the center. So again, there is an equivalence here in the magnetic field distribution here at the surface between a distributed source of this kind and a dipole. So that means if you then measure a dipolar field pattern like this, and you subject it to a dipole model, and you fit a dipole either here on the left, then it will fit perfectly well. So this one dipole might explain 100% of your data, even though in this case the data were generated by this distributed source. But it will also fit perfectly in the case when it was produced by a dipole. And the other way around, if you take these data and you compute something that we call minimum norm estimates, we haven't really talked about yet, but it's one way of estimating a distributed source like that. In this case, because the data were produced by a source like that, you will get it back, so you can estimate that accurately. But it will also produce exactly the same solution when the data were actually generated by a focal dipole. I mean, it simply doesn't know anything better. It was told to produce a distributed source and that fits with the data. That's what it does. And then, of course, there are other types of minimum norm estimates. But the idea is whatever you do, if the data look exactly the same, you will get the same result in both cases. And of course, now the crux of the story is usually we don't know where the data really came from. So we start with data like that, and we simply have to accept that if two types of sources produce the same data, then no method can distinguish between the two. So we can only distinguish between the two with a priori assumptions about whether we, for example, if we know that it was a focal source, or we suspect that it was a focal source, and you can fit your dipole. But if somebody else wants to claim, no, this activity was produced by a distributed source, the evidence cannot distinguish between the two. And here that sounds like maybe with EEG and MEG, you simply cannot do anything, so you can't really localize, or it's always ambiguous. But of course, the data do pose some constraint on the current distribution. It's not like that anything goes. And I would just like to give you some examples here, just to cheer you up a little bit, maybe. So we had these examples in the previous presentation. So imagine you present your some checkerboards to the left visual field of your participant. So what we would expect is something in visual cortex here, maybe a bit more activity on the right in the contralateral hemisphere. And if we look at the topographies in sensor space, this is EEG, these are magnetometers, and it looks like at least it's approximately correct. So there's a larger amplitude on the right here with this widespread MEG topography, a bit harder to see, but the dipole, if you already expect a dipole, then this will be somewhere here on the right. Yes, but now if we now apply our minimum norm method to the data, then we can be, it actually confirms in this case that it right lateralized here in visual cortex. I mean, visual cortex is usually quite a nice, or occipital cortex, quite a nice area to study with MEG. It's close to the sensors, good coverage. So this is the kind of spatial resolution you can expect. It is probably just a small patch of cortex somewhere that produces this activity. It is a bit more distributed. Also, if we would look at the bottom of the brain, you would see a bit more distributed source, but it's clearly right lateralized. So this confirms that we have a very lateralized response, and it is an occipital cortex. Another example, auditorily evoked activity. Again, if you present a tone to the right ear, you expect stronger response in the left hemisphere. And we know that the response somewhere in primary auditory cortex is probably just a few square millimeters. So we can fit this potentially with a dipole. And in this sample data set here, this is confirmed, first of all, in sensor space. So we get rather widespread topography here. So if we didn't know where this activity came from, I mean, it wouldn't be obvious here from the EEG response. And in fact, the peak is actually somewhere in the back of the brain. So you might mistake that for a visual response even. If you look at the MEG, you can imagine a dipole pointing downwards here in the gap. So if you have some idea of what produced this activity, you can already guess with some accuracy where the real sources are. And if you then use source estimation and you use produce the kind of solution that produces the minimum norm, then you do get some confirmation that it must at least come from close to auditory cortex. I mean, the peak, interestingly, is in the middle temporal lobe. So there you go. Because auditory cortex is a little bit deeper down here in the Sylvian fissure. So that is something we will have to talk about later. But you can see it's left lateralized, and at least it's confined to an area around in the proximity of auditory cortex. So that means, yes, and I should also say that this method here did not make any assumptions about the location or the number of sources. So it really just took the data and tried to find a sensible distribution of activity across the cortex. So more about that in the next few sessions. But I hope that shows us that we are not able to scan the brain with millimeter or even below millimeter precision. It is not just up to us to simply say we spent more money on a bigger scanner and we can get deeper into the brain or we can get better spatial resolution. There are some fundamental limits, but this is the kind of spatial resolution you can expect from your source estimates.